My talk is in the context of the prediction of soil loss as an aid to making land management decisions to conserve soil. The key factors are climate, soil topography and land use, and there are many new soil loss models that, when applied to the prediction of erosion in agricultural land, produce widely differing results. Most of the models have been developed because the developers perceive inadequacies in the universal soil loss equation. As many people know, the universal soil loss equation was developed in the United States using more than 10,000 plot years, and it predicts the average annual soil loss in terms of 6 factors. The concept of the unit plot is central to the mathematical operation of the USLE. The unit plot is analogous to the control plot that's included in field experiments, where the control plot is the base condition. In the case of the universal soil loss, the unit plot focuses on climate and soil conditions. Once that has been dealt with, then the other factors come into play to account for non-unit plot situations. Consequently, the USLE model works in 2 mathematical steps. The R factor is given by the long-term average annual value of the EI30 index. It's where E is the event energy and I30 is the maximum 30-minute intensity. That relationship came from work done by Wishmer and Smith in 1958, and the slope of the regression line in this case depends on the susceptibility of the soil to erosion. However, in the USLE, K is given by the total soil loss divided by the total EI30 over the period of time, and this avoids using regression analysis and also enables the unit plot data to be predicted accurately. Consequently, the USLE equation for event soil loss on a unit plot underpins the USLE models. Soil loss is only measured when runoff occurs, but the USLE does not take this into account. However, the USLE works because runoff is empirically related to EI30. This is a graph of event soil loss against EI30 on a plot at Morris, Minnesota. As you can see, it's somewhat different to what Wishmer and Smith observed. And if we look at that in terms of logarithmic scales, you can see that EI30 tends to overpredict low soil loss and underpredict high soil loss. As an alternative to using the EI30, you can look at soil loss in terms of runoff and event sediment concentration. And if you do that, you can see that the event sediment concentration is given by EI30 divided by runoff amount. If you actually look at the data empirically, soil loss event sediment concentrations are better related to EI30 divided by event rainfall. You then get this event erosivity index, which you can rewrite so that the event erosivity index is QR, the runoff ratio, times EI30. And that is what's used in the USLEM. And note that you have to have a change in the erodibility index to account for that change in the erosivity index. If we go back to that plot that was at Morris, Minnesota, as you can see, using the QREI30 index, gives a much better relationship to soil loss than when EI30 is. This is the Nash-Sutcliffe efficiency factor plotted for the two models. The top one is for the USLEM and the dotted line is for the USLE. And basically what here shows that the USLE model works well when the runoff coefficients are high, but less well when the runoff coefficients are low, as in the case of Morris, Minnesota. Various people have developed various alternatives to EI30, including runoff. This is one set that have been used in the APEX model and developed by Williams. The problem with this model is that the K factor should vary for each one of these indices, but it does not. Within year variations of erodibility occur, and this can be looked at in terms of the unit plot with EI30 and an event erodibility index for each storm. In Russell 2, this event erodibility index is considered to vary through time through the effect of climate and soil moisture. And this is the relationship that they have attained for that plot at Morris, Minnesota. Here we have a design storm that can be used to look at how that particular function works. And if we look at the Russell, we have EI30 times KE, but in the USLEM we don't have an event erosivity index evident. However, you can rewrite that equation, and so you still have EI30 as the erosivity index, and erodibility is given by the product of QR and the erodibility, long-term erodibility for the USLEM. If you compare those two models for those design storms, you can see that the within-year peaks in soil loss are much greater with the USLEM. Many years ago, WEP was suggested as an alternative to Russell 2, or the universal soil loss equation, and that was because USLE-based models do not take account of the fact that inter-rill erosion is dominated by raindrop energy, while rill erosion is dominated by flow energy. So WEP was provided as a model that models rill erosion and the movement of soil from inter-rill erosion areas to rills. Its capacity to predict bare fallow runoff soil loss plot data is a matter that needs to be considered if MEP is to replace USLE-based models. Now, if we look at the Russell K, as we saw earlier, it's the total soil loss divided by the total EI30. You can actually predict the total soil loss in terms of by WEP, and then use that as an alternative to the observed. When this was done, this result produced discrepancies that were blamed on input data error, causing the WEP not to predict the observed soil loss totals well. You can calibrate WEP to overcome this problem. If you do so, you can look at WEP as a predictor of event soil loss on bare fallow areas. And here's examples from 4 plots in the USA. Again, an Nash-Sutcliffe efficiency factor is considered here, with 1 being the perfect model and a negative value being for a bad model. And in 3 of the 4 cases, WEP shows up to be a bad model. On the contrary, Russell 2 produces positive results in all 4 cases. As if you look at the USLEM, all locations produce a good result. Now, the thing about this particular situation here is that web uses predicted runoff and cannot run with observed runoff, so the data for the USM is done on the same basis. As you can see, if you use observed runoff, you will get much better efficiency, modeling efficiencies. Runoff is a factor that will contribute to errors because it has to be predicted in predicting events or loss. Over time, databases have been developed to compare Russell and Webb in the USA. This is a case where that was done in 2016. The question that arises here is that large differences will affect land management decisions if Webb is used. So the red ones will indicate people would be told to reduce using those ones, and the green one would encourage them. More intensive modelling in Iowa recently showed that disparities related climate soils and management options, and this shows the disparities related to soils. Differences result in both input and model differences in this case. And one of the issues about model differences is that USLE focuses on plain areas where rill erosion occurs intermittently after sheet erosion, whereas WEP focuses on crops grown on ridges where rill flow and rills are always going to occur. So, both Russell 2 and WEP are wrong, but when it comes to looking at soil loss predictions as an aid to making land decisions, WEP is perceived to be more wrong than Russell 2. Consequently, Russell 2 remains as the official aid to making land management decisions in the USA.